Audio check. Check 1, 2. Audio cut out? Alright. Coming back in. Hold on 1 second. And that's how I started my class. That's how I started this recording. Yes. Check. Check. 1, 2. Can you hear? Ah, Cougar. You told me the audio was out, and then you told me it was in. Whatever. All right, it's fine. It's fine. Can you hear? You guys can hear? All right, so check this out. What we're going to be doing is we're moving on to Exponential 2. I told you that this stuff is going to go really quickly, and I hope that it does because I want to try to at least talk about all 14 chapters before we move on to stats, and we only have like 2 months to do 14 chapters of exponentials and 5 chapters of stats. So we got our work cut out for us. But anyway, this exercise that I'm doing right now is just like the table exercise that we did in the previous lesson, although it looks a little bit different. These are what exponential graphs look like. They look like these radical curves that kind of like shoot up all of a sudden. Let me go over to Desmos and see what we can do. Desmos, come on. Come on, Desmos. There we go. Come on. You can do it. All right. So as we've investigated before, and and I think that I'm going faster than what they're, the slow way they want to introduce this to you. But we're looking at 2 to the x power or something like that. We're looking at graphs that look like this. It shoots up really quickly like this. And no, there is no horizontal or vertical asymptote that this thing never ends up touching. It just happens to go up really quickly. So when will it reach out over here where x is equal to 100? Well, the y value will be very, 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 very big. I mean, if you think about it, that's 2 to the 100th power. You're multiplying 2 by itself 100 times. That's a big number, even if it's a small number like 2. So all we got to figure out now is, well, what exactly are these numbers that we want to talk about? Like, is it 3? Is it 4? Is it 5? And what can you tell me about these numbers as I change them? If A is 1, oops, let me zoom out a little bit. No, not 1. But if A is 2, here's what the graph looks like. Got it? If A is 3, here's what the graph looks like. What can you tell me about the difference between 2 to the x and 3 to the x? What's the difference between the blue graph and the red graph? And think back to when we were doing rational functions and even quadratics. As I change A, what happens? Come on, you guys, can you hear me? At least let me know you can hear me. Yes, I can hear you, Mr. Balde. No, I can't hear you. Yes. Okay, all right. What happens to A? It gets wider. Sorry, the phone call just called now. I don't want to have it think. I don't want you to think that it gets wider or skinnier. But what I've always told you is it's like the gummy bears. It goes back to these gummy bears. What I'm doing to the blue graph to make it into the red graph is I'm taking it and I'm stretching it vertically. Do you see why when we're dealing with parabolas we were doing, like instead of saying skinnier and fatter, I said vertically stretched and vertically compressed? This is the reason why I'm coming back to that vocabulary now, is because in order to, the difference between the blue graph and the red graph, I can even make the red graph more extreme, like 5. You know what? T would be nice. There, I can change T And you can see that as the number gets bigger, you vertically stretch it. Can you guys see that? And as it gets smaller, it gets closer to that blue graph. Now what happens when it gets to 1? It levels out. Why is it a straight line? If you don't know, say IDK. Yeah, because exactly, Erica, because anything to the 1 power, 1 to the anything power, not anything to 1, but 1 to the anything power is 1. Like 1 to the 10th power is 1 times 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 1. That's equal to 1. Now, as I make this a fraction, what do you see? It goes the other way. Okay, so it's instead of exponential growth, we're talking about exponential decay. It dies down exponentially. And that happens when you're talking about a fraction, like 1/2, 1/6, all of that kind of stuff. What happens if I make it negative? What happens to the graph? Oh, it disappears. Really? Why does it disappear? Huh. What is -2 to the x power? Oh, I don't know why it disappeared. But basically, what happens to it? What's the difference between the blue graph and the purple graph? It flips it over. Yeah, exactly. It just flips it over. This is exactly like what we were dealing with when we were talking about parabolas and rational functions. You almost should be used to seeing graphs and how they behave like this. The same behavior goes the same way. I think that's cool. But anyway, let's move on. Because you don't think it's cool. Because you guys are like, oh, Mr. Daldy, you're just doing it again. Anyway, let's figure out what number should go here. If this number is 6 and this number is 18, what's the next number that should go there? $54. Awesome. Erica, how did you figure that out? You saw that the jumps were 3, right? To get from 6 to 18, I had to multiply by 3. To get to the next number, I should multiply by 3 again. So it's multiplying by 3. Now, how did you figure out that the jumps was 3? I guess you just ask yourself, what times 6 gives me 18? Is that what's going on? $18 over 6. Yeah, exactly. You divided 18 divided by 6, and then you get 3. And you say, oh, the jump is 3. That's good. That's a good technique, because let's check out number 2. Okay? If we want to make a little table, x, f of x, using the numbers they gave us, 0, 100, 1, 110, okay? 2 what? This one's a little bit tougher. 121. Very good. How'd you figure that one out, Elijah? Well, let's talk about same process exactly. The only thing is, it's not a pretty number like 3. The jump to get from here to here, you can figure out that jump by doing 110 over 100, which is equal to 11 over 10, which I have no idea what that is equal to in terms of 1.1. So in order to get to the next number, you multiply by 11 over 10, or 1.1. There we go. And if you want to keep on going, you get 1.1, blah, blah, blah. Cool? All right, let's do number 3. This time what I'm doing is I'm giving you a number at the end. I'm giving you these two numbers over here. I'm going to make a table. I want to figure out what 0 is. I'm giving you 110 and I'm giving you 220. What is this number over here? What is a previous number right here, number 3? A blank spot. 5. Very good. I know, this one's a little weirder. No, it's not that weird. You know, if you divide 20 by 10, you'll get 5, right? Or no, you'll get 2. 20 divided by 10 is 2. So you know that in order to get from here to here, you have to multiply by 2. What would you have to multiply by 2 in order to get 10? Well, the answer would be 5. You have to multiply by 5 by 2 in order to get 10. So you guys see how we're playing, we're putting the pieces into this puzzle? All right, let's try number 4. Number 4 looks tough. Okay, so I'm going to make my little table. You don't need to make the table. I'm just making the table so it's easier to see. Negative 1, 1, 0, comma what? And 1, comma 49. So how would I do that? What is this question mark here? What is this number that I should put in here? All right, I'm going to do that same process, but this time I'm going to do f of 1 divided by f of negative 1, which is equal to 49 divided by 1, which is equal to 49. So in order to get from here to here, I had to multiply by 49, right? Well, how do I get from here to here? Multiplying by 49 once to make a jump of 2 spaces is the same as multiplying by what? Twice. Can you hear me? There we go, Kaylin. Exactly. In order to make this jump of 49, I had to multiply this by 7 and multiply that by 7 as well. So this 1 times 7 is 7. Does that make sense? So my answer here that I would put in for this spot right here is 7. Essentially, it's the same thing. If I make a jump and go from here to here and I had to multiply by 49, it would be the same as multiplying by 7 twice. Does that make sense? That's what I'm saying. Awesome. Awesome. Do you guys feel like you guys got this a little bit better? So there's like 13 problems on this one. Let's do something a little bit harder. Let's do this one. Number 10. We're dealing with exponential decay this time. So, just as a question, what does that tell me? I know that the form of the equation is a to the x power. If I'm dealing with exponential decay, what is that telling me about the value of a? Is it a big number? Is it a small number? Is it a negative number? Is it a small negative number? Is it a big negative number? Is it 1? Is it 0? What can you tell me about a? And I showed you this on Desmos. Do you remember? I just showed it to you like 10 minutes ago. Not even 10 minutes ago. It would be 1. No, it won't be 1. If a were 1, it would be a flat line. Right? Because 1 to the x power is a flat line. It's a negative number. No, I disagree with you there as well, because negative numbers would just flip this thing over. It won't give you this The exponential is negative. All right, we'll try that. Ah, yes, you're right. The exponential is negative. Do you guys remember what happens when you have a negative in the exponent? No? Oh, okay, well, I'll tell you. You flip it, it's a reciprocal, exactly. See, look, see this purple graph? It's the same exact thing as 1/2 to the x power. That purple graph and the blue graph, or the orange graph, the purple graph and the orange graph are the exact same. That negative takes the thing over here that it's acting upon and flips it over. So the thing that it's acting upon is 2, or also known as 2 over 1. 2, wait, did I do that right? Yeah, I did. 2 over 1 to the x power is the same. Oh, no. I need a negative there. There we go. Can't hear. All right, logging out, logging back in. This would be 3. Yeah, right. How's that? Can you hear me? I'm glad we're talking about this because I think this is really important. All right. Essentially, all I'm saying is, for that number 10, that I know that I'm going to be taking a fraction to the x power, because if I'm dealing with a fraction, then I have this exponential decay. Anyway, that's neither here nor there. Let's talk about how do I get from if I made a little table of the values that they gave me, x, f of x, then I'm looking at negative 122, 0 comma what, and 1 comma 5.5. How would you guys figure out what that middle number is? What I would do is I would do f of 1 divided by f of negative 1. I always do the bigger number on top, or not the bigger number, but the, like 1 is bigger than negative 1, that's what I mean. I always do the further to the right on top and then the one on the left on the bottom. So this would be 5.5 divided by 22. Can anyone tell me what 5.5 divided by 22 is? 0.25, also known as 1/4, people. So if I'm jumping from here to here, and I had to multiply by 1/4, how did I get from here to here and here to here? I multiplied by 1/2. Because 1/2 multiplied by 1/2 is the same as 1/4. So apparently, you just take this number divided by 2, so you get 11. So the answer that should go right here is 11. I can also tell you that if I were to graph this on Desmos, I would tell Desmos, okay, Desmos, I want you to graph, actually, let's see. Yeah. Actually, this is what my graph is. If I were to make this into a table, let's see what it does. Negative 122, 0, 11, 1, 5.5, 2, 2.75, negative 2, 44. Okay, cool. So I actually made their graph right here. This is that graph. It's the orange one. It's not the purple one. I guess I figured that out because I was looking at the purple one. I was thinking, huh, the y-intercept of the purple one is at 1. Whereas the y-intercept of my graph that I want to graph, this guy right here, is at 11. So I guess I should multiply my graph by 11, or my equation by 11. That's why instead of graphing 1/2 to the x power, I graphed 11 times 1/2 to the x power. So apparently that's the equation for this thing. Am I speaking crazy to you, or does this make sense? Awesome. Your homework is going to just have a whole bunch of these kinds of things. There is one thing I wanted to cover with you before I left you guys for the day, and I think I got to leave you guys pretty soon. But I did want to cover some exponential rules with you, and this might be review. I don't remember exactly how much exponential rules I got with you, but just as a review, just so you guys can remember, this is apparently I covered this with you before because this is under the warm-up section, but x to the 5th power times x to the 3rd power. This is called the sum of exponentials. Essentially all it is, and you can print this up and complete the table, or at least take notes. This is x to the 8th power. If you have the same base but different exponents, then you can add the exponents together and keep that base. So the base over here is x and the base over here is x, and the different exponents is 5 and 3, so I can basically keep x as the base and then add 5 plus 3. You guys remember this, right? Alright. X to the 8th power over x squared, that's essentially the same as x to the 8th power times x to the negative 2 power. See, this negative in the exponent will drop that thing down. This is saying the exact same thing. And if I were to use this sum of, the sum of powers, that's just x to the 6th power, because you add 8 plus negative 2. This technically is called the quotient of powers with the same base, but, I mean, really, it's the same thing. Now, if you bring an exponent to an exponent, like x cubed to the 4th power, that's simply x to the 12th power. You're not adding those exponents, you're multiplying them together. I know I showed you this before, but I'm just trying to remind you. Let's see. X to the 0th power is what? What is x to the 0th power? It's 1. Exactly. Anything, and this is going back to what I first taught you, anything to the 0th power is 1. Alright, let's try this. 2/3 squared, what is that? Well, this, essentially what you're dealing with is 2/3 times 2/3, which is 4/9. Now, you're thinking, that wasn't very hard at all. And my answer is, no, that wasn't very hard at all. But you would not believe how many people do this. They only square the numerator and they forget about squaring the denominator. This is entirely wrong. Do that, and I will personally come down and boot you in the face. Got it? Luckily for you, I don't wear boots, so I guess I'll rubber slipper you in the face. Alright, let's try this one. 3 times x to the 7th power cubed. Again, we need to make sure we distribute that cube into each thing. So that what you're looking at is 3 cubed times x to the 7th power cubed as well, which is 3 times 3 times 3 is 81, and then x to the 7th power cubed is x to the 21st power. That's not a 4, that's a 21. Okay. X to the negative fifth power. Well, we already kind of covered this before. When we're dealing with negative exponents, all we got to do is reciprocate whatever it's acting upon. So that's just 1 over x to the fifth power. I can turn that negative exponent into a positive exponent as long as I flip it over, put it downstairs. If I have 1/5 to the negative 3 power, I can make that into the positive 3 power if I just take the thing that I'm acting upon it and flip it over. So instead of 1/5, I have 5 over 1, which is also known as 5 cubed over 1 cubed, which is known as 125. We cool? All right, let's do 2 more. X to the a times the 1/2, or to the 1 over a. Oh, that's pretty simple. That's just x. I mean, essentially, that just comes back to this thing right here. An exponent to an exponent, you just multiply them together. Well, a times 1 over a is known as 1, which is also known as just x. We cool? All right, this one might look a little funky. It's not bad at all. C times a times x plus 1 over c times a to the x. Okay, here's what we're doing, okay? Obviously, the c will cancel out with the c. We're good with that, right? And I can make this thing as a times x plus 1, that's the numerator, times a to the negative x. We're cool with that? I've made it to the negative x because I just took this thing in the denominator and I wanted to put it in the numerator, and so in order to do that, I would have had to make the exponent negative. Well, now I'm just using the product of powers, and I can just add, oh, okay, well, that's the same base, different exponents. I can just say a times x plus 1 plus negative x. These are all in the exponents right here, all up on top. Oh, that's just a to the first power. That's also known as a. See this complicated equation right here? It's really just a secret code for a. You guys got it? And this is a warm-up. This should be familiar to you. You should know all of this stuff already. I'm only doing this because I want to make sure that you guys got this. Oh, shoot. You know what? We already finished exponential 2, and that warm-up that I just gave you was talking about exponential 3. Literally, in 40 minutes, or an hour, in the 1 hour that we've been working on this, I covered 3 chapters with you. Well, 2 chapters and part of 1. So, yeah, we're going to get to this pretty quickly. This homework is not that bad. It's pretty straightforward. It's important for you to do. I'm almost tempted to say the best thing for you to do. I would say I don't have time to make all of this homework. But what I would do if you want to become boss at math, and it's not even that bad, is print out this homework, or print out Expo 1, Expo 2, Expo 3, and do every single problem in there. Which is essentially kind of what I'm going through with you. I'm not going to finish off. I'm going to stop the class now because I don't have any time. But anyway, I'll see you guys later. You guys all right? All right. Okay. Talk to you later. Bye.